Yep, here we are once again. It's the physics video lecture. Psci 168, video lecture 16. What are we talking about today? We are talking about conservation of energy, and we're moving on into hydropower. So a lot of great stuff, and I'm going to have to try to keep the lectures a little shorter because I intend to send you guys out to find many images, download images, include them in your book, right? Your lecture notes are supposed to turn into a book, and it'll have many colorful pictures. But we're talking about conservation of energy, so I'll write that down. Very important. Energy is neither created nor destroyed. It changes form, and we've learned about some of the forms of energy and their transformations already. We have the asteroid collision. We have the grandfather clock. So from there, we have a perfect segue into hydropower. And I sent out two images that I wanted you guys to print out. I'm going to hold them up to the camera right here. I have them along. And typically I'd have them up there on a screen and we could talk about them. But instead, I'll just discuss them briefly. I'll make some kind of rough sketch. So the first image is called, images here that we're starting with. The first one is called the water crane, and it's just a big water wheel. I forget what year it is, I used to know. Anyway, it's a very large water wheel, and it's being used to lift things. So I'm going to hold this up to the camera. There we go. Huge. We can do a close-up at the bottom. And there's the guy in the booth. Point B up there is where the water's coming from. Okay, that's a little. There we go. Good, so that's the one. You can get some screenshots from that, but definitely print it out and have a good look at it. The second one that I'm going to discuss, and I'll hold up right now, is called Perpetual Motion. And these are these old style woodcuts from centuries ago. This next one is from 1673. The other one's probably at least as old. So perpetual motion. And I'll hold it up, and I'm going to encourage you guys to take a close look at what's going on in this contraption. Okay, see, there's the text. There's the knife grinder, and there's a mechanical contraption with water wheel with a tank of water up there at A. Okay. Good. That's the best we're going to do under these circumstances. So you want to have a really good look at these. As far as the water crane goes, we have a very large water wheel, and there is water coming out of a spout, turning the thing. There's a fellow up there in a booth controlling some levers, and this water wheel has a very large axle here, with some chain around it, lifting a bucket. Okay. Now we're going to analyze this thing in greater detail. In fact, that's a horrible picture. How about if we just do a side view of a water wheel? By the way, I should also say, in addition to these images here that you want to print out and have for your book, I'll just put right here, homework, while I have your attention. You want to locate some good water wheel imagery, okay? Water wheel images. Because I'm going to begin with the analysis here right now. And I have some slides I usually show, but it's actually going to be better if you guys go out and discover these things on your own. You'll probably find some good ones. So here is a water wheel. The water crane is a historical example. So a water wheel, how is this thing a machine and how much power can it deliver? That's what we want to know. So you could have this wheel here, it's got an axle, there's a trough coming from a higher place that delivers water to this thing, and you know the water is collected here, and then when it turns the wheel, in our case counterclockwise, I can even bring some. So we've got water flowing down here. At this point it starts to fill the buckets, and then it gets dropped down to this lower level, which roughly corresponds to the diameter of the wheel. Okay, roughly corresponds to the diameter of the wheel. And if you're thinking about energy and potential energy and work, let's get another color here into the mix. Then you would have an axis here, and you would have the top of the wheel and the bottom of the wheel, and that H that we're always talking about, the height through which, in this case, our water drops is H. Okay. So that's actually all I need to know. Well, I need to know H, and I need to know the flow rate of the water. Now, there's flow rate of the water. So how many kilograms per second in kilograms per second? Very important. So if I know this flow rate, I'll underline that, then I can give you the horsepower of this thing. Okay. So this water wheel turning counterclockwise, hooked up to an axis in some way, and then you somehow take power off of that axle. So this is what we're looking for, some water wheel images in real life that embody this principle. There's going to be a tank of water somewhere, but you've got water coming in, some channel of some sort, and then it turns the wheel. Okay, so that's the principle of the water wheel, and that's basically what's going on with the water crane. So this was, again, this was our water crane. Now the perpetual motion machine, it's so complicated I can't really draw it that well, okay? And you guys will print it out and study it. But let's call this perpetual motion machine. Perpetual motion idea. You can be sure that it can't really be made to function the way people want. The idea was this: the water wheel has water coming in from somewhere, but what if the stream dries up? Okay. What if you could have a tank of water that turns the water wheel, does some work, and yet with the work from the water wheel, you lift the water back up into the tank so that it runs forever. Okay. That's what we were looking at. So in that case, I'll just do a rough schematic. You've got the tank of water, there it is, and you've got a water wheel here, which I could hope to draw, but not really. You've got water coming out Okay, you've got water up here, you've got water shooting out and turning this wheel counterclockwise, kind of out towards the class here. So far so good. Okay, you could even say this lower basin of water is some distance h below the upper one. Okay, now I can't really draw all these gears and so forth, but the whole purpose of this contraption, all the stuff that I can't draw here, is to lift the water back up into the tank so that it will just cycle through. And they're thinking, well, look, we can get work off of this wheel, maybe we can get enough work to lift the water back up into the tank. Now, if you remember our discussion of the bouncing ball and the pendulum last time, we should realize the very best possible case would be to lift all the water back into the tank, but as soon as you tried to get some extra work off of that axle, you would no longer be able to lift all the water back up into the tank. Okay, that's the limiting case, and in fact, friction is going to not allow it. So have a good look at the perpetual motion idea, that perpetual motion image. All of that complicated stuff, well, I can draw part of it. There's what's called an Archimedean screw. That's a tube. These are actually used, they actually exist, that kind of has a threaded channel inside, and if you hold it in the bottom of the water and you turn it, it will carry the water back up. So those are actually in use in the world, the Archimedean screw. But all the gears and all that complicated stuff, you can follow it. It's conceptualized so that it actually does work. You can follow it all and see how the water's being cycled up. And you've got the guy sitting here grinding the knives on the grinding wheel, which is connected to here as well. Okay, that's my drawing. You guys study it. So this represents a point in history where the idea and the reality of water wheels had existed for a long time, and people were trying to construct a perpetual motion machine out of that. In order to make further progress, you have to realize that's not possible. On the other hand, if you have water in a tank, you can definitely get useful work out of it. So the water wheel is very useful. It's one of the all-time original machines, we could call it that. And we just have to separate the possible and practical and what's impossible about this. So that's our continued discussion of conservation of energy, which we're going to leave at this point. Okay, I hope I made that point clear enough. It'll come up in other situations as well. Good. So yeah, have a good look at those. Get yourself some images, water wheel images, and now let's talk about hydropower as it's actually practiced and utilized. Consult the clock here. Very good. So you already know what you're looking for, some water wheel images. Now I'm going to just draw a dam and discuss the basic issues here. We'll spend a couple of hours on this. You can say this is really a central topic in the entire semester. Everything we do can be discussed in terms of this. So I'll start with everything we do this semester can expand on this hydropower discussion. So here we go, hydropower. That's our topic. So what I start with is a dam that's holding back a volume of water. Okay, so there's a dam and it holds back water. We've got colors. So there's a lake behind the dam. Okay. There's a lake. There's a dam. And this is something we're going to get plenty of images of. I can go into some of the different types of dams, which is really interesting and impressive and important. You've probably seen some yourselves. But for the moment, this dam is maybe across a canyon or something. It's holding back a large volume of water. So if you refer the surface of that water to some lower point, down here I'm going to draw a powerhouse. Okay. And what we're going to do is have water flowing down this channel here, goes through the powerhouse, turns all kinds of machines. We don't even really have to know how they work yet. And it is discharged into a lower lake. So this is a lower reservoir. And here's the upper one, this lake, the upper reservoir. Okay. So there is a height difference in my picture, and the difference between this level here and the level of the lower reservoir allows us to measure the potential energy of the water in the lake. So let's go ahead and extend this line out here. This is our favorite letter H, the height difference. And the water in the lake has potential energy with respect to this lower lake. Okay. So why does the water in the upper reservoir represent potential energy, capacity to do work? It's because it is elevated. Okay. If it were just a lake in the plain, it would not represent any energy. It's elevated. So the elevated water in the upper lake has potential energy. Just use the letter W the way we often do, and that's the mass of the water times G times H. So now we've learned that the mass of the water times the gravitational acceleration, that's the weight, that's the weight of the water times H. Okay. So we, of course, we're now used to using M times G, right? That's our force times H, and you could measure this potential energy. Okay. If you knew the density of the water and the volume of the lake, and you could say how many joules of potential energy. This may be a good time to fill in a bit of material here. So, mass of water, actually let's use density. Density of water is equal to 1,000, pretty sure I said this before, kilograms per cubic meter. And again, there's a meter stick, you make a giant cube like this, you have 1,000 kilograms of water. So that way you can see how you get the mass. To get the mass of water, you multiply the density times the volume. So this Greek letter, remember we printed out our Greek letters for a reason. So the Greek letter rho is mass, I'll use capital M, per volume, capital V. So mass is equal to density times volume. I'm going to immediately do a calculation like that, because once you do one of these, you can always see how to do that. Okay. going to do this in a slightly different order than I usually do. In fact, let's clean this up a bit. So density is mass per volume. You may want to even write that down in words. I'm just going to rewrite what I got there. Okay. So mass, by just cross multiplying, I just multiply both sides by V is equal to density times volume. Density times volume, we'll say capital M. We could have a capital M up here, by the way, right? Is equal to density times volume. So let's immediately do an example. Let V equal 2 meters times, let's make up some easy number, times 1 meter times 5 meters. So there's a tank that's a meter times 5 meters times 2 meters, okay? There's a meter stick, so 2 is about from where I'm standing to a bit above my head, and then 5 meters, okay? So you can visualize that. So what is that? That's 2 times 1 times 5 is 10 cubic meters, and the mass of water, and M is going to be equal to 1,000 kilograms per cubic meter times 10 cubic meters. You see, I chose easy numbers. Do this with a different color. The cubic meters cancel, so you're left with kilograms. And what do we have here? 10,000, or 10 to the 4th power kilograms. Once the numbers get too large, we just use scientific notation, right? So 10 to the 4 kilograms. So we can extend this. This could be 2,000 meters. Okay? It could be really big. Doesn't matter. We can just calculate it out, get the meters cubed, multiply by 1,000. So we can figure out the mass of the water in our reservoir. We multiply that by G, which is 9.8 or 10, close to 10, and multiply it by H, that height difference, and that will give us the joules. So let's erase this guy here. So continuing this thought here, and right, we're just working with this. You may even want to put a capital M in here just to make sure you see, what we're relating. But so continuing, suppose H equals 100 meters. Okay. Let G, it's approximately 10 meters per second squared, right? So we're just going to multiply these things together, and we're talking about this tank here, but of course it could be a lake as well. Then the energy is equal to this mgh, and approximately 10 to the 4 kilograms times 10 meters per second squared times 100 meters. Okay, I chose some nice numbers, didn't I? So what do we get here? Equals 10 to the 4, 5, 6, 7. 10 to the 7 what? Okay, well we're using, whenever we use kilograms, meters, and seconds consistently, these are newtons times meters equals joules, okay? 10 to the 7 joules. Like I said, you can do this with any size of tank you want. This reservoir could be a couple thousand meters long and maybe 100 meters deep. Okay. You'll notice I haven't, and we'll talk about this more, but I haven't put the powerhouse, I haven't labeled it yet, but I haven't put it right at the bottom of the dam. That's because you can run this pipe far down the mountain to where you finally put the powerhouse. Okay, that will be part of our discussion. But like I said, I'm doing a slightly different order now. I'm just focusing on how much energy is in that lake. You can make up any numbers you want. Now I'm going to relate joules to kilowatt hours. Every time you pay your energy bill at the end of the month, if you look at it before you pay it, it tells you how many kilowatt hours you used of electricity, and it'll tell you about the gas you used as well. We're just talking about the electricity for the moment. That's where the kilowatt hour unit comes up. So, yeah, we got some room right here. So what I'm going to talk about next, so now I have the energy as my example that we have in our tank of water, which is just a lake, okay, or the other way around, lake, which is a tank of water. So those are joules. Now I think I do need a little more room here. But we'll keep the picture of the dam for the moment. So, now we have to recall that power equals work over time. Power was energy over time, and the unit was the watt, right? So watts equals joules per second. Okay, so we learned that already back with the grandfather clock, watts and the stair climb. Watts equals joules per second. So joules equals watts times seconds. Okay, so watts equals joules per second. So if I multiply my watts times my seconds, I get joules. Okay. And the other way to write that is, so joules equals watts times seconds, or energy equals power times time. Energy equals power times time. Now it's not about kilowatt hours, and we're just about there. Okay, let's get rid of this picture. So what we can say now is that energy equals watts times seconds. Actually, let me, since I've written that already. Now let's look at what is a kilowatt hour. The kilowatt hour. Okay, so you're used to paying for the kilowatt hour, and it's written like this: kilowatt hour, KWH, anywhere from a dime to a quarter or more. So what is a kilowatt hour? Well, kilowatt hour, kilo is 1,000, and watts are what they are, right? An hour, or 1 hour, 1 hour equals 60 minutes, multiply that by 60 seconds equals 3,600 seconds. Okay, so 1 kilowatt hour equals 1,000 watts times 3,600 seconds. And watts times seconds, did I write it here? Watts times seconds is equal to joules, okay? So 1 kilowatt hour is an important one, so it's good that we use a lot of board on it. 1 kilowatt hour equals 3.6 times 10 to the 6 joules. Okay, this is one you want to know, but if you know these definitions, you can just figure it out even if you haven't memorized it, okay? You just kilowatt hour work per minute. So 3.6 times 10 to the 6 seconds. So our tank of water had 10 to the 7 joules worth of energy because it was elevated by 100 meters. So how many kilowatt hours is this? Okay, 3.6 times 10 to the 6 is less than 10 to the 7. It goes into there, it goes in about 3 times. It's just under 3 kilowatt hours. So this is an important skill for us because we can easily multiply up our joules, but we can just as easily convert to kilowatt hours. And then we know how much water, how much energy that reservoir holds. Okay, I'm going to consult the clock. Let's see how we want to round this out. Good. So I will make a couple of homework problems right now. This is the kind where you'd leave enough room in your notes so that you can figure it out. And if you can't do it, or if you want to know the answer, just tell me in an email and I'll do it at the board the way I've been doing. Good. So let's turn this into a couple of homework problems. And you know, if we can do a couple, we'll be fine. So we have everything there. So homework, let's just make reservoir has, so we have a reservoir, it's a big tank, it's like the lake in my picture there, dimensions of say 1,000 meters times 400 meters times, how deep is it going to be? 30 meters deep. Okay, that's our reservoir. So what do we want? Volume. 2, mass of the water. And before we do that, let's formulate the rest. Reservoir dimensions, and it's located H equals, these are real numbers, so let's say 500 meters above the lower lake, or above the powerhouse. Okay, so that's the situation. So here's what we want to know. We want to find the volume of the reservoir. We want to find the mass of the water in it, just the way I did my example for you. We want to find the potential energy in joules. Potential energy in joules. And 4, the potential energy in kilowatt hours. So if we can do that, we can do anything. Okay, that's all we have to be able to do, well, for starters at any rate. And like I said, this example I had here, I'll even continue on with another. So 10 to the 7 joules. Here's how you would do that. You would actually just continue this, and here's our conversion factor. So we would say times 1 kilowatt hour divided by 3.6 times 10 to the 6 joules. Okay, that's how you always do these conversions. Let's get rid of this box here and make a bigger one. Okay. That's all you do. You just express this conversion factor as a 1. You could also do the conversion in the opposite direction for a different problem. Okay. But you see the joules are going to cancel. So 1 kilowatt hour equals 3.6 times 10 to the 6 joules. And then when you do that division, you're going to have some number slightly less than 3. Okay? Slightly less than 3. So once you've done this, you can figure out this one as well. Now this is going to be a few kilowatt hours, which you'll use in a day, say, or less. But the kilowatt hours in this reservoir are actually going to power a town for some time. It's going to be a much bigger number, so you're going to express it in scientific notation. Okay, I'm about to wrap things up, but let me just do one more thing. I'm going to reiterate our picture just to make sure we see where we're headed with this. Okay. This was just an aside to teach us how to estimate the energy in the lake, so we'll be confident. So I'm just going to redraw our lake. We're going to do this, this little cartoon we're going to do many times. Many times. There's the dam, there's the lake. Actually, this tube here that carries the water down to the powerhouse is called the penstock. So I'll put that terminology here. Got the lower reservoir. We've got the upper reservoir. This is called the penstock. So that's some terminology you can look up. Penstock, that's that tube here that's going to carry the water down to there. And of course we have that height difference h that is utterly crucial. That's how we calculate the potential energy. So what we're going to do with this next is discuss how the water flows through here, gets enormous pressure, gets enormous speed, and it can turn turbines, it can generate electricity, it can do a lot of things. And what we'll do is we'll keep adding stuff to this picture as we learn about it. So right now we've just talked about the water and its potential energy. So we know that in principle there are so and so many kilowatt hours worth of energy up there. And as we go through with the whole discussion, we'll figure out how to get it down to our civilization and run our stuff. So that's where we're headed with this. There's a lot to say about this, and you guys will be able to get great pictures of all this material as we develop it. Good, so see you guys next time.